Hello, I'm your host, Dr. David Urban, and I will be guiding you through Brown and Poon's Introduction to Organic Chemistry, 6th edition. The slides were downloaded from the Wiley Instructor Companion site and are copyrighted by Wiley. The commentary is my own. I have divided each chapter into smaller sections to make it easier to view on a wide variety of platforms. So let's begin. We will finish up Chapter 5, Part 7, Reactions of Alkynes. Okay, so alkenes had two pi's, p orbitals that overlap to form a single pi bond. Alkynes have two p orbitals that allow it to form two double bonds. Okay, so the first thing we saw in the differences between alkenes and alkynes is the fact that the hydrogen at the end is more acidic than any of the other hydrocarbons. Okay, so if we look at our pKa's and we compare water to our alkyne here, water has a pKa of 15.7. Okay, so water can be either acidic or basic, and so getting rid of that hydrogen has a pKa value of 15.7. Okay, so if we think about water as being kind of neutral, and now alkyne is our next one up, it has a pKa of 25. Okay, so it's not really acidic. It wouldn't cause, corrosive damage, but it is easy to remove. It's not that much more higher up than water is, okay? But now if we take that sp hybridized carbon and convert it into an sp2 hybridized carbon, the acidity decreases again, okay? Our pKa jumps up to 44. That means it's even less acidic than it was before. And if we go all the way from an sp2 all the way down to an sp3 hybridized carbon, the acidity drops one more time to one of our least acidic compounds right here at a pK of 51 would be just like an alkane right here. Okay, so this is sp hybridized, this is sp2 hybridized, and this is sp3 hybridized. So the sp character of the triple bond of the alkyne gives it its acidity. Okay, so let's think about how we can do this right here. Most of the time when we deprotonate acetylene, we use something like sodium amide, okay? And the reason we use sodium amide is because it's a very strong base. Let's try to remove that proton using something like hydroxide, which was what we think of as a very strong base in water. If we try to do that, let's look at our acetylene here. It has a pKa of 25 right here. And if we use what we consider a strong base to try to remove that proton, and it does remove that proton and creates our acetylide ion right here, what we end up creating is our new acid, right? So our weak acid became our new base, and our base became our new acid. If we look at the pKa of this acid, water, our pKa of that acid is 15.7, okay? So 15.7, that's a lower number. That means it's a stronger acid, okay? So by deprotonating our weak acid here, we generate a stronger acid. What do we know about acid-base equilibrium that tells us whether or not this is going to happen? Okay, remember when we're talking about acid-base conjugate pairs, we always want to form the weaker acid in the product, okay? So if we did this reaction, the weaker acid would actually be shifting the equilibrium to the starting materials, not the product. So we would have acetylene and hydroxide ion would be the major component of that solution. That being said, we can't do these reactions of deprotonating the alkyne in water because we would generate this as our component. Okay, so most of the time we will see these done in the absence of water and using sodium amide as our base to make this acetylide ion. Now that we have this acetylide ion and we know we don't form it in water, we use sodium amide, let's do some reactions with it, okay? So acetylide ion, it's an anion, it has a negative charge, and so it is not only a strong base, but it is what we call a nucleophile. It's looking for positive charge, okay? As a nucleophile, it can donate that pair of electrons that makes the negative charge to an electrophilic carbon or a carbon with a partially positive charge to generate a new carbon-carbon bond and a byproduct. So in the case of, we've generated our acetylene ion, and we have a sodium as our counter ion here. We're using the electrons from the negative charge to form our new sigma bond, this new sigma bond, and we've displaced chlorine from the product, giving us a salt of sodium chloride. Okay. So we're using the carbon anion as a way to create a new sigma bond. Okay. So in this case, the electrophile is only partially positive because we have a polarized chlorine carbon bond. It comes in and these electrons kick out with the sodium and we have our new sodium bond. Okay. This is the first time we've made a carbon-carbon bond. Okay. So we've actually made this carbon-carbon bond by breaking a carbon halogen bond. And we're going to see this in chapter 7 as well, halo alkanes. Okay, because the alkyl group was added to the original alkyne, this reaction is called an alkylation. So we've added the methyl group, this methyl alkyl, to that alkyne. Anytime we add an alkyl group to a compound, we call that an alkylation. Okay, so let's look at the importance of the alkylation in acetylide ions. Okay. So acetylene is actually a gas. It only has 2 carbons in it, but you can use that to your advantage to build bigger and bigger compounds. So for example, if we take acetylene, react it with sodium amide right here to generate our acetylide ion, and then react it with something that we can create a new sigma bond with, we can actually make that new carbon-carbon bond. And now we've gone from 2 carbons and 2 carbons to our new species that has 4 carbons in it. So we're building longer and longer carbon chains or carbon skeletons. And then we still have an acidic proton, so we can do it again. And then we can add something of a different size. Notice this has 3 carbons in it now. This one only had 2 carbons in it. And so now we've added our 2 carbons in the first reaction. We added 3 carbons in our second reaction. And so now we have a total of 7 carbons long, and we still have our triple bond to do additional chemistry. Okay, now we'll talk about all the different reactions here in chapter 7, but the general concept is we're using this acetylide ion to create bigger and bigger carbon chains by reacting it with polarized carbon halogen bonds to where we can go longer and longer and longer chains. Okay, so one of the other things we can do with alkynes is to reduce them down with hydrogen, just like alkenes, okay? So if we take the same reaction conditions it took to take an alkene to an alkane, we will take an alkyne all the way down to an alkane. So our triple bond gets reduced all the way down to sp3 hybridized, fully saturated hydrocarbon, okay? Now, if you don't want to get all the way down to that saturated hydrocarbon, if you want to stop at an alkene because you only want to destroy one of those pi bonds by adding hydrogen across it, you have to do something very special. You have to reduce the reactivity of your catalyst, okay? So when we do this, we do what we call Lindlers catalyst, and technically we call it poisoning the catalyst, because what it does is it takes the palladium metal and it gets modified with lead salts. That lead salt poisons the catalyst, so it's not reactive enough to reduce down an alkene. It's only reactive enough to reduce down the alkyne. So it'll add hydrogen across a triple bond, but not a double bond. So we have to use Lindlers Class or a poison catalyst to be able to do that. Just like the regular catalytic reduction, it's still syn addition because we're still at the surface of a metal, but it's reduced reactivity, so it'll only add across a triple bond and not a double bond. And so we typically get cis alkenes out of this because the hydrogens are added to the same side. So we'll get cis alkenes stereospecifically using a Lindlers or poisoned catalyst. All right, that's the last of the reactions we're going to talk about for alkenes and alkynes in this chapter. Continue on with chapter number 6 in the next video.